the next type of analysis that we're going to look at is ANOVA, analysis of variance. So to do an analysis of variance, we'll get some sample data. I'll look at one of my recently used files, and we will look at, what shall we look at? How about insurance claims? That seems like that will be fun. So open up insurance claims, and we have a whole bunch of different kinds of insurance claims. And we've got a couple of different quantitative variables: incident date and claim amount, and policy date and coverage and deductible. So let's say, and then we've got some nominal variables here, right? So claim amount, claim type. That looks promising. So let's see. So there are several different claim types, 5 of them, not in any particular order. So that's a great idea for an ANOVA. And there are, so let's see if there's different amounts of coverage for different claim types. So we'll do analyze, compare means, one-way ANOVA, and we'll do type of claim as our factor, and we will do amount of coverage as our dependent list. And that is all we're going to look at for now. So we hit OK. Well, no, we do options. We want descriptive statistics for sure. So we do continue. Do we want to do a post-hoc test? Sure, let's do a post-hoc test. We'll do the Tukey honest significant differences post-hoc test. This is, in my opinion, the most useful post-hoc test. This will let us compare the different groups to each other. Okay. Continue. Now we hit OK. So we look at our ANOVA first, and we see that there are no average. There's no difference between any of the groups. This is a non-significant ANOVA. F ratio is 0.4. The variation within and the variance is smaller than the variance within. So this is not a particularly good example. That is too bad. There's a lot of those, huh? So if we were going to do, so in the Tukey test, what that did is it found the mean between wind and hail and all the others, and it did that for each of these. So it found each pairwise comparison and found a standard error and looked to see if they were close to each other or not. And then it put them together in the order of their averages. So contamination is the thing that people had the highest coverage for. And it, since none of them were different from each other, put them into one subset. If these had been low and these had been high, then maybe there would have been 2 subsets with like these 3, this one, and maybe these 2 and this one, but there was not. So if we're going to do a graph for ANOVA, we do graphs, chart builder, pick a bar plot, and let's see, amount of coverage goes in the y-axis, claim type goes in the x-axis. We got a mean. I like error bars. I want the error bars to be standard errors, and I hit OK. And there is our bar chart. Oh, I want to get rid of the title. Do just like titles. Goodbye title. There we go. Better. So that was one way of doing things. And then if we were going to do a results for ANOVA, we would go into some complicated details about that. So you go to Word. So I have a picture here. And since this is non-significant, oops, that didn't copy correctly. Let's just right click, that'll work. There we go. Paste. So say there. What is that? Oh. There were no significant differences in the amount of coverage among the different types of claims. F4, because there's 5 groups. 4, 4410. Our subscript. equals what was it, 0.418. P equals 0.796. Now, normally you wouldn't need to report any of the group means, but just for example, then what you would do is you'd say claims of the contamination type had the largest mean amount of coverage, mean plus standard error, equals 321 21007, because it's in hundreds of thousands of dollars, plus standard error is 9075. Oh, it's in thousands, sorry. So 9075. And water damage claims had the smallest amount of coverage on average. And so then we don't have to write mean plus standard error this time. We can just say, okay, 294142. 94142 plus 12435. 12435. And we can see those really big standard errors are why these things are not that different from each other. You don't have to put the columns in there. It seems to make sense in this case. All right, that's how you do it in ANOVA.